This is your presenter Asloop Mudassar, and I am presenting slide number 101 of the course on laser physics. Question is, discuss briefly the most common longitudinal and transverse pumping techniques. The answer is, first we discuss longitudinal pumping. For longitudinal pumping using laser beam from a single strip diode, it is preferable that the beam incident on the active medium must have a circular spot with the diameter compatible with the cross-sectional area of the active medium. Which may be in the range from 200 micrometer to 2 millimeter. So this could be the possible area of cross-sectional area for an active medium. So our laser spot must be of these dimensions. Three most common longitudinal pumping geometries are discussed. Figure 101.1 shows a plano-concave resonator pumped longitudinally as a single-ended pumping technique. The caption of the figure is schematic diagram of single-ended longitudinal pumping in a plano-concave resonator. You can see that an active medium is placed between a concave mirror and a spherical lens. So a spherical lens is actually used to convert the input beam or to focus the input beam onto the active medium. The cavity is actually formed by the plane mirror at one end of the active medium and by the concave by the plane mirror on left end of the active medium and the concave mirror on the right end of the active medium. So this will form the resonator cavity in which the active medium is placed. The spherical lenses will just focus the beam from single strip diode laser through spherical lens onto the active medium, so that the spot of the laser beam being focused on the active medium should have the same dimension, approximately the same dimension as that of the cross-sectional area of the active medium. A plane mirror is there and a concave mirror on the other side of the resonator form two ends of the resonator, in which an active medium is placed as shown. The resonator axis is also pointed out, and the direction of the input beam from the single strip diode laser is shown with the two arrows as an input beam. So this is a longitudinal way of pumping the active medium, because the light which is being focused on the active medium is along the direction of the resonator. And this is a single-ended pumping technique because the pumping is done only from one side of the resonator. So in this case, from the left side of the resonator. So that's why it is called a single-ended pumping technique. The pump beam enters the resonator along the resonator axis from one of the resonator mirrors. The pump beam may be collimated or may have slight divergence or slightly convergent beams. So the three possibles are there. The beam could either be perfectly collimated with the and matching and it's in the spot size of the beam matches with nearly the cross-sectional area of the active medium. The second option is that the beam is slightly divergent or the beam is slightly convergent. So these are the three possibilities. Figure 10.2 shows a ring laser in a folded configuration pumped longitudinally as a double-ended pumping technique. So since this is a double-ended pumping technique, it means that the pumping is done from the two sides. So for example, from the left side, you can see the pump beam received by a spherical lens, and the spherical lens will focus the pump beam onto the active medium placed over here. And on the right hand side, you can also see a pump beam being focused by a spherical lens onto the active medium. So the two pump beams, so this is the double-ended longitudinal pumping. and longitudinal in the sense that it is along the direction of the resonator cavity or the axis of the resonator cavity. So you can see that there are two concave mirrors on either side of the active medium, and they reflect the light towards the plane mirrors, and then from the plane mirrors the light will enter into the active medium. So in this way the path is completed. That is, the light from the concave mirror will be focused on one of the mirror of one of the plane mirrors, and then from this plane mirror the beam is diverted to another plane mirror, and from that plane mirror the beam is diverted towards another concave mirror, and from that concave mirror to the active medium, and through the active medium to the concave mirror from which we started the discussion. So in this way the resonator is formed, and this is called folded ring laser configuration. Folded in the sense because the beam is being folded over here. This is the folding region of the two beams. The caption of the figure is a schematic diagram of double-ended longitudinal pumping in a folded ring laser configuration. So of course, in the advantage of this one with the single-ended configuration is that you can deposit more power into the active medium. And the two sources which are being used to pump the active medium are independent sources. That is, the source on the left hand side providing a pump beam is independent of the source providing pump beam on the from the right hand side. The active medium is pumped longitudinally along the resonator axis from opposite sides with the two different pump diode sources. The spherical lenses focus the two pump beams at the center of the active medium rod. Figure 101.3 shows a Z-shaped folded linear cavity pumped longitudinally as a double-ended pumping technique. The two pump beams are focused at the center of the active medium rod along the resonator axis from opposite sides with the two different pump sources. So this is the description of the figure number 3. The caption of the figure is schematic diagram of double-ended longitudinally pumping for a Z-shaped resonator. You can see that pump beam is hitting the spherical lens from the left, and the spherical lens will focus the pump beam from one of the diode laser at the center of the active medium placed at the center of the resonator. And from the right hand side, you can see that another pump beam is provided by another independent diode source, and which is received by a spherical lens, and the spherical lens will focus this pump beam onto the center of the active medium. So the two spherical lenses are used to couple the input beam from the diode sources onto the resonator at the center of the active medium. The cavity is formed by the two plane mirrors at the extreme end of the Z-shaped resonator, and there are two concave mirror also, which completes the structure of the resonator. So if we start from one of the plane mirror at the top, the light from this plane mirror will hit the concave mirror. The concave mirror will divert the light through the active medium to another concave mirror, and that concave mirror will focus the light onto the plane mirror. This plane mirror will reflect the beam backward and back on the same path, and then of course the concave mirror will pass and from the concave mirror the light is reflected through the active medium to another concave mirror, and from this concave mirror the light is focused onto the plane mirror from where we started. So in this way one round trip is formed within the resonator cavity. So the resonator cavity is formed by the two plane mirrors and by the two concave mirrors. And of course, this scheme is again the double-ended scheme because the pumping is being done from the two sides. This technique provides Z-shaped technique provides more control over the parameters of the cavity. Next, one example of transverse pumping is presented. An ND-YAG rod diameter 4 mm, length 50 mm is radially pumped by 3 pump modules symmetrically placed around the rod. So let me show you that figure. For example, this is the figure. You can see that an ND-YAG rod is placed in the center vertically, shown vertically over here. And you see that there are 3 modules of fiber symmetrically placed around the ND-YAG rod, each containing 16 fiber modules, and these are independent fiber modules. The length of each module is 32 mm, whereas the dimensions of the rod is 50 millimeter long. There is a jacket of rods of the pipes through which the water will flow in order to cool down the temperature of the ND-YAG rod. The caption of the figure is schematic diagram of transverse pumping. The ND-YAG rod by 3 modules of fibers arranged symmetrically about the rod. So you can see that there are 3 independent fiber modules consisting of 16 fibers each, symmetrically and transversely pumping the ND-YAG rod. So let's complete the description by reading through the paragraphs. There are 16 fibers in each module arranged side by side with 2 mm center to center spacing. The width of each module is 32 mm. Each fiber in the module has 800 micrometer core diameter and a numerical aperture of 0.22. On one side of the fiber module, an array of diodes injects a total power of 10 watt, and the output from the module directly illuminates the laser rod. 3 different arrays of diodes are used. The laser rod is cooled by flowing water in tubes arranged longitudinally around the rod. Light reflects against each module around the rod are used for increased pumping transfer efficiency, which is reported around the 80%. The meaning is that when the three array of fibers, each consisting of 16 fibers, illuminate the rod, then of course some light is reflected off the rods. That reflected light is also can also be focused onto the rod by using other reflectors. So this way the pumping efficiency can be increased, and it has been found that the pumping efficiency around 80% can be achieved in this case. For uniform illumination of the rod, because if the fiber modules are very close to each other, the pumping may be slightly non-uniform, because when the ends of the fibers which are close to the rod, they provide more intense beam, and of course the beam will diverge out from each fiber. So on the other side away from the center of the fiber, the beam slightly fall in intensity. So if we want to have a uniform illumination of the rod, the distance between the modules, that is the distance between the fiber modules and the rod, can be increased at the cost of decrease in pumping transfer efficiency. But you know that the advantage is that the pumping will be uniform, but the disadvantage is that the pumping efficiency is reduced. The figure 4 shows the transverse pumping mechanism for an ND-YAG rod with 3 fiber modules. Each of 5 fiber modules can also be used for increased optical output power. So you see that I have shown only 3 modules of fibers, but in order to increase the efficiency of the system, the researchers have also reported to use 5 pairs of modules of the fibers to pump the ND-YAG laser. So this will increase a deposit of huge energy at the anti-jag rod, resulting in the increased optical power from the anti-jag laser. So you see that here I have presented 3 longitudinal pumping techniques. This one is the simpler one as given in equation number 1. This is a single-ended longitudinal pumping techniques. This is, you see that the double-ended longitudinal pumping technique in a folded ring laser configuration. The quality of the laser beam coming out from this is more refined as compared with the previous one in terms of laser parameters. And this is the scheme, again double-ended longitudinal pumping is Z-shaped resonator. So this also provides better quality of the beam as compared with the previous two. And then the last one, which is the transverse pumping, is also provided using anti-jag rod illuminated by 3 pair of 16 fiber modules symmetrically placed around the anti-jag rod. But you see that we are not here going to discuss the advantages of these technique or the disadvantages of these techniques in terms of the characteristics of the lasers coming out from these configurations. Maybe if we could spare time, if I could spare time, I would be able I could be able to also discuss the characteristic of the laser beams coming out from each individual such configurations, giving the advantages and the disadvantages of each system. So this completes my answer. So this is the end of slide number 101.